Hello everyone, I'm Esranur Karacif and I'm excited to present our work named A Methodology for Material-Based Computational Design supported by mobile augmented reality application. This work was developed in the PhD course titled Special Topics in Architectural Design Computing, run by Associate Professor Sevil Yazıcı at Istanbul Technical University Architectural Design Computing Graduate Program. This is the general framework of the study. First of all, I would like to express the key terms used in this work, then purpose of the study, literature review, methodology, and finally the conclusion. What is material-based computational design? Material-based computational design is a set of computational strategies supporting the integration of form, material, and structure through performance analysis and fabrication. Form, material, and structure are all taken into account comprehensively in the material-based computational design approach. The target group in this study is architecture students. The architecture students generally and rarely take into account material and structural performance challenges into their design solutions at the early design stage. And there are emerging technologies which are capable of improving the design processes since they expand traditional techniques of design and making, such as augmented reality. Why should mobile augmented reality, or shortly MAR applications, be used in design education? As I mentioned before, they expand traditional techniques of design and making. They can be superimposed on a real environment, which makes the design environment more dynamic and interactive. An AR interface can be controlled by hand and body movements in space. It offers real-time feedback. The tools utilized for AR applications are freely accessible via mobile devices. Users could examine their designs for a particular environment by using MAR technology to evaluate designs that were simulated in the actual site context. By employing this technique, designers can increase design efficiency. AR technologies make it simple to collaborate, facilitate social interaction, and integrate digital information with mobile computing. Additionally, they gain flexibility in the design process, allowing them to work with multiple digital models and scales. In this study, the employment of more applications in MCD enables evaluating and changing material, structural, and performance-related properties without disrupting the physical model. Thus, it's possible to analyze material qualities, structural systems, and building performance comprehensively. A real-time, synchronized, interactive MAR interface enables the perception of non-visible information about a building. By rotating the building, the architecture students can manipulate it as though it were a 3D item using the computer's 2D interface. The purpose of this study is to construct a model at the preliminary design stage based on material, structure, and performance data in order to enable synchronization via a MAR interface. This would aid architecture students in design process and help them comprehend design from a broad perspective. 292 research papers published between 2010 and 2022 are examined for the literature review in Science Direct, International Symposium on Augmented Reality, Google Scholar, and Communicate database. The lack of literature is primarily the tactility followed by convertibility between the materials. The proposal of MAR integrated MCD, in the current study enables convertibility and tactility by utilizing a variety of building materials. So a mobile augmented reality application is proposed in order to fill a gap in the literature connected to architectural design, construction, and related educational approaches. The study's methodology entails superimposing three elements: material properties, structural system, and building performance analysis onto a physical model with a MAR interface, and three visual prototypes are proposed. At the beginning of the study, a physical model is required. This model should be translated into a digital model and integrated with rhinoceros by pre-identified QR codes on the hologram SDK. This enables the users to recognize the object being worked on. Three different inputs, material properties, structural analysis, and building performance analysis, are added to this physical model by a mobile augmented reality application interface, and as a result, these analyses appear separately or optionally overlapped on the smartphone screen. Thus, the user can observe the effect of a digital intervention made on the physical model synchronously through simulations. Finally, the user would receive the necessary information from these three visual mockups. The case study prototype of the graphical user interface is a skeletal construction with horizontal and vertical parts like columns and beams that offers a straightforward structural plan for prototyping. To make the system simpler and more flexible, the flooring is excluded. The hologram SDK includes pre-identified QR codes for each type of beam or column. As an illustration, the dimensions of a particular beam or column as modeled in the rhinoceros grasshopper environment appear on the screen when the QR code on that beam or column is scanned. Once the modeling and classification of each stick in the rhinoceros grasshopper environment have been completed, the application can be launched. The mobile application will be used and tested in the latter stages of this study. The visual interface prototype is developed in this stage of the study, and a methodology is proposed for the following stages of this work. So the first set of inputs required pertains to three material attributes. The type of material is one crucial piece of information that the user needs to enter. This could be fundamental building elements like steel, wood, or reinforced concrete. The other data which should be entered by the user is the color of the material, and the last one is the texture of the material. These three features can be altered directly through the MR interface without any intervention on the physical model. The ability to improvise in design is made possible by moving the beams or columns. This makes it possible for a more adaptable working environment. On the other hand, because of the type, color, or texture of the material specifications can place limitations on the composition of the design. The type of the structural element should be entered by searching from the applications library, which includes types of the structural elements such as steel, wood, and reinforced concrete, similar to how the material specifications section is performed. For instance, options like H profile and U profile show up if steel is chosen. The dimensions of this particular structural piece are entered in the subsequent tab. The behavior of the structure, which is modeled on Karamba and simultaneously is sent to the application via the hologram SDK, is seen on the MAR application screen. The building performance interface, which is linked to the Ladybug and Butterfly tools for the simulations and simultaneously brought back to the screen, should be filled out with information such as the position and direction of the prevalent wind. Users can compare these three different forms of data side by side or independently. They are able to be incorporated into their context and surroundings, and in that environment, simulations customized to the performance of buildings can be run. This makes it possible to calculate numerous architectural design, construction, and performance factors. In conclusion, the capabilities of integrated approach are improved by using emerging technologies in architectural design. This technology helps the target group not only visualize the data from the developed models, but it also allows them to interact with the model and improve the design before it's implemented. 3D models can be interacted with in a more flexible setting with AR. The experiment of designing with real and virtual items is enhanced by AR. The creative design process can be improved by experimenting with and changing actual and virtual items together. As a comprehensive and coordinated design production tool, this decision support system offers to incorporate the material, structure, and performance characteristics of physical and digital models into design. The decision-making processes in design are successfully supported by haptic and digital interaction, creating a 3D interactive model and experiencing the digital results in a real-time environment. And finally, the graphical user interface, the methodology, and the conceptual framework are the sole components that are designed and offered in this research. The mobile application will be created and tested in the latter stages of this study. These are the main references we used in this study. And thank you very much for listening.